Ladies and gentlemen, Your Royal Highnesses, dear Jungfrau, it is with great pleasure that we welcome all of you today to the fourth event of the Science Next program, Water Futures. I'm Özgü, a former laureate of the Jungfrau contest myself, and I'm a current science student at the University of Luxembourg. And I represented Luxembourg in the European Union contest for young scientists in 2018. And therefore, today I'm very happy to be here again with the Jungfrau. I will be moderating the conference this afternoon, and for technical reasons, we will be having the conference in English, but please feel free to stop me at any moment and ask any questions that you might have, and if you don't understand what is meant or said. So we'll all help and translate as best as we can. And at the end of the conference, you can ask any of your questions in Luxembourgish, English, French, or German. And yeah, so stellt Frauen op Luxembourgisch, Deutsch oder Französisch. So please don't be shy. Considering the difficult circumstances that we find ourselves in with the ongoing pandemic for the past 2 years, I feel very privileged to be here today on this occasion. And for that, I think we owe gratitude to scientists and those who support scientists. However, the global health crisis that we've been battling with as mankind did not hit pause for the growing concerns regarding other issues on a global scale, such as loss of biodiversity, climate change, rise in sea levels, water pollution, and ocean acidification that we're all familiar with. And to be honest, these issues all seem to be interconnected and can be traced back to increasing demand for an unsustainable and unstable management of non-renewable resources. So before I hand over the microphone to our scientists, I would like to invite Carlo Hansen, the president of the Fondation Jeune Scientifique Luxembourg. And Carlo has been supporting research and science for over the past 20 years, and he's been the president of the foundation for the past 14 years. So I would like to please invite him with a big round of applause to the stage.
Your Royal Highnesses, dear young scientists, distinguished guests, welcome, good afternoon. Your Royal Highnesses, we are honored by your presence today, but also thankful for your and Princess Stephanie's interest and encouragement. Thank you all for joining us today. I am extremely pleased to welcome Mrs. Mara Manieri, a former Jungfrau laureate, and of course, Dr. Laurent Pfister. Thank you both for being here today. Mara participated in the National Jungfrau contest in 2020. For her science project, she took water samples from Luxembourg's rivers and streams and analyzed the impact of fertilizers and manure on the water quality. She was awarded in 2020 the participation at Europe's largest science contest, the European Union Contest for Young Scientists, organized by the European Commission. She is co-founder of a group called Change in the Lycée Classique de Diekirch, a group which aims at raising students' awareness to environmental issues, to sustainability, and how to protect environment. She also participated at the Luxembourg Biologies Olympiade. Dr. Laurent Pfister is head of the research unit Environmental Sensing and Modeling called Envision at the Luxembourg Institute of Science and Technology. He studied at the Université de Strasbourg and has a PhD in hydrology and water resources and is accredited to supervise research. He is a lecturer at the University of Luxembourg, author of numerous publications and associate editor of science journals. He is a group leader of a research team, the Catchment and Exo Hydrology, which focuses on water catchments, water collection, storage, mixing and release, using to this experimental hydrology, like for example, biological tracers or infrared imagery. As you see, Mrs. Manieri and Dr. Pfister have a common scientific interest for one of Earth's most valuable resources, water. Water concerns all of us, and its management arises a lot of questions. How do we protect and guarantee its quality? How do we ensure that everyone has access to it or keeps access to clean and potable water? Its management and protection requires that everyone takes a real interest in the issues at hand: droughts, floods, modification of water quality, and the loss of biodiversity it entails. Remember, last year's floods in July, Echternach was partially down under, as well as the province de Luxembourg or the Ahrtal. So we should care about water, a crucial resource we have the responsibility to protect and manage wisely. Everyone can contribute to do this, and I'm very proud to say that each year there are young people who present a scientific project at our annual national contest, which precisely aims at the protection of our planet's resources. The National Young Forscher Contest, which exists since 1971, is not a talent show. It's a think tank, a tool for young people who want to make a difference by contributing through their projects to search for solutions, for answers, and to tackle those global issues, or at least explore possibilities how to solve these global issues we must face. Thus, the Science Next program our foundation offers since last year, thanks to one of our sponsors, is to be understood as an additional tool for all those who want to participate at the contest or intend to do so. The workshops and the conferences offered in Science Next program all aim at helping to reflect on issues, at documenting an observation, at doing a survey or an experiment or an invention, which brings us further and benefits all. So that's the gist of the Young Forscher National Contest and the Science Next program, which goes with it. Enjoy the conference, and I give the floor to Mrs. Susanna Young. Thank you very much.
Thank you so much, dear Carlo. Your Royal Highnesses, distinguished guests, dear young Forscher, we are extremely grateful to welcome all of you for the opening of the fourth event of our brand new program called Science Next. So before starting, may I deliver some more information about Science Next, which is hosting actually the Water Futures conference tonight. Thanks to our sponsors, Science Next has been launched on November 2021 and is since accessible for free at the benefit of all registered students in Luxembourg aged between 11 and 21. Composed of an extracurricular training cycle throughout the school year, Science Next provides with a syllabus that guides our young scientific enthusiasts from a starting idea of a project up to a public presentation of an scientific achievement, as it happens tonight with the coming conference. Ever since, some of our students I see present tonight, you have already learned about how to transform a simple idea into a successful project, how to make proper research on a specific topic, and how to structure the ideas into an impactful presentation. These tools are acquired by you, our young students, on different occasions at focus places where you actually meet real experts and scientists, such as Paul Wurtincup Science Center, Luxembourg Institute of Science and Technology, and so on. But most importantly, Science Next is also a place to have fun, right? We had so much fun together. And not to mention that Science Next is also a place to be connected with your peers. So after all these wonderful experiences, today you will have the opportunity to see an example on how to present your project in a scientific manner. By offering this conference, Science Next is willing to show, based upon the example of our dear former laureate, Mara Manieri, but also Dr. Laurent Fischer, that your personal reflections can really contribute to the current challenges of our planet, and that you can really make the difference. Last but not least, I really need to address many thanks to our sponsors, to the board member of the FGSL, to Mr. Serge Quazzotti, the president of the jury of the contest, and a special recognition goes to Mr. Sébastien Wirtz. Thank you all for your incredible dedication, not only to this platform, but far beyond. Thank you so much, and enjoy the conference.
Thank you, Susanna, for this introduction. So, as Carlo had mentioned, now we will welcome Dr. Laurent Fischer and Mara to provide us with their outlook of different generations of scientists on the same topic, water, of course. They will develop on innovative instruments and protocols and offer environmental data with unprecedented temporal and spatial resolutions, which provide brand new information on how climate change is intensifying the hydrological cycle and signals in flood records. Now, I would like to invite Mara to the stage to hear about her outlook and presentation of her research. Please, everyone, welcome Mara with a big round of applause.
Hello, my name is Mara Manieri. Until last summer, I was a student of the Lycée Classique de Diekirch in the north of the country, and I'm now studying medicine in Munich. In 2020, I participated in the Young Forscher contest with a project realized in 2019. I am here this evening to talk about the project, the competition, and what followed. The project is entitled Water Quality in Luxembourg and its Effects on Aquatic Microorganisms. I live in a rural area, and so I have kind of always wondered about the effects of excrements on the water in rivers and streams, but also on the microorganisms living there. And when I learned about La Fondation Jeune Scientifique and the competition, there was an opportunity to search for answers. I wanted to begin with some preliminary explanations. So the majority of terrestrial gases are nitrogen. This element is necessary for the formation of organic molecules that are essential for life on Earth. I'm sorry. I think we have to switch microphones. Yes? So, yes. I'm very sorry for the technical problem. So the majority of terrestrial gases are nitrogen. This element is necessary for the formation of organic molecules that are essential for life on Earth, such as proteins. However, most organisms can't directly use the atmospheric nitrogen. But we also find it under different forms, such as organic nitrogenous molecules. Via several processes, these can be transformed into nitrate NO2 and nitrate NO3. These two ions are very soluble in water. The organic nitrogenous molecules come from dead organisms and from animal excretions and feces. Naturally, the concentration of nitrates and nitrates in water is relatively low, and so without human intervention, they constitute a limiting element for plant growth and development. Phosphorus is another essential component of life. It can be found in nature as phosphate anions, PO4. Animals release the phosphate when their organisms break down, so after their death, or through their excretions and feces. The phosphate is relatively scarce in soils and consists therefore a limiting element for plants' growth and development as well. To increase the amount of nitrogen and phosphate available, nitrogen and phosphorus fertilizers are used in agriculture. They are then no longer a limiting element for plants' growth and development, but stimulate the development of cultivated plants. These numbers were the data I found during the preliminary research in 2019. The latest official StatTech statistics on fertilizer use in Luxembourg date from 2010. However, these figures do not consider organic fertilizers, manure, or green manures, which are nevertheless very widely used, especially by farmers with animal farms. So the real volume of nitrogen and phosphorus fertilizers is still much higher. There are quite strict regulations for the use of nitrogen fertilizers, both mineral and organic. Minimum distances to watercourses and wells have to be observed. And these are greater for organic fertilizers than mineral ones. The use is also subjected to the weather. And finally, it is forbidden to apply fertilizers to the fields between the 15th of November, 15th of February. The regulations, however, vary depending on the areas under consideration. Water protection areas, such as around the Lac La Haute-Sur, are subjected to stricter regulations. The Geoportal also indicates information on the state of rivers. They indicate an average concentration and the maximum concentration measured. However, this does not make it possible to follow the evolution of the different concentrations over the year and to conclude on the impact of agriculture. Moreover, at the time of my research, the latest published figures dated from 2017. So, to put it plainly, in some parts of the country, it is forbidden to put manure on the fields, as well as during certain periods of the year, especially from the 15th of November to the 15th of February. But regulations on fertilizer use are not an end in itself. They should seek to preserve water quality. So I thought that we should recognize by analyzing the water if we are in a fertilizer ban period or not, just as we should recognize if we are in a water protection area or not. But why do we seek to preserve water quality by fertilizer regulations? To allow aquatic life, not to hinder the proper functioning of the ecosystems. But what does exactly happen then when the water quality decreases? How do the organisms react? Do they vary in number? Do they vary in species? Generally, I thought that we should expect a decrease in the number of microorganisms observed when the water quality decreases. And just a little explanation. In this project, I define good water quality as low concentrations of nitrates, and phosphates, whereas bad water quality equals a high concentration of nitrates, and phosphates. In reality, it's naturally more complex than that. So the project itself consists of two different parts. The first part is about water quality of the rivers, and the second one is about the impact of bad water quality to aquatic microorganisms. For the first part, I took samples from different rivers across the country, and the exact locations are shown on the map. I tested these water samples for the presence and, where applicable, the concentration of nitrates, and phosphates, these by aquarium tests. And for the second part of the project, different amounts of slurry were added to water sampled from a pond. 24 hours afterwards, the water was analyzed under the microscope and the microorganisms were counted in a hemocytometer. And in order to know the water quality in the different containers well, that water was also analyzed for the nitrates, and phosphate. So here are the results of the river water analysis. From the 9th to the 11th of November, it was still possible to apply fertilizers to the fields, whereas the samples taken from the 15th to the 17th of November were taken during the fertilizer ban period. It was found that the average before phosphate concentration is 0.15 milligram per liter lower than the average after phosphate concentration. The before average nitrate concentration is 2.5 milligram per liter higher than the after average nitrate concentration. I was unable to detect nitrate, probably, while that doesn't mean that there weren't any, but probably the concentrations were just too low for the aquarium test, which were then not sensitive enough. And samples from the water protection areas, so the sample from the Lac La Haute-Sur only shows residual concentrations of the measured ions. And to evaluate the effect of manure on aquatic microorganisms, I used the hemocytometer to estimate the abundance and size of the different microorganisms, and the results are shown on the left in the table. The nitrate, and phosphate concentrations in the different containers are shown on the right in the diagram. The results showed that in the containers with no or little slurry, we could find mainly microorganisms that could be described as large or very large. On the contrary, in the containers with several milliliters of slurry, there were mainly microorganisms that could be classified as small or very small. These classifications are quite random. However, the microorganisms classified as very small are in the order of magnitude of bacteria. So thus, there is a bacterial proliferation if the water contains a lot of animal detritus, while non-bacterial aquatic microorganisms die. To conclude, in terms of river water quality, it can be said that in periods with a fertilizer ban, the nitrate concentrations decrease. The water in the water protection zones, so the water of the Lac de la Haute-Sur, has the lowest concentration of nitrates and phosphate measured. In terms of impact of manure on aquatic microorganisms, it can be said that the populations evolve differently in water of different quality. Water with a lot of organic detritus kills non-bacterial microorganisms while it stimulates bacterial proliferation. In summary, therefore, my research has confirmed that the regulation of fertilizer use has a real impact on water quality and aquatic population. So this was the project I participated in the Jungforscher competition with. Shortly before the competition itself, Luxembourg came to its pandemic-induced stop and the jury sessions were switched online. And thankfully, I was very honored to be awarded the participation prize at the European Union Contest for Young Scientists, called for UCIS in Salamanca, Spain. It is organized by the European Commission, and it is the biggest and most prestigious science competition in the EU. Initially planned to happen on September 2020, it was cancelled, so we couldn't travel to Spain, sadly, but we had a very beautiful alternative prize ceremony. And last year, the UCIS committee announced that they were organizing a combined UCIS, where they were combining the UCIS 2020 and UCIS 2021 under a hybrid version. So the Spanish contestants were in Salamanca, while the international contestants participated via an online platform, and the contestants from 2020, so including me, could participate nevertheless. And while online contests aren't exactly the same experience as contests in real life, at least it was made possible that we could have an international contest with intercultural exchanges. And meeting other scientists working in the same field is a very enriching experience and a lot of fun. So participating in the Jungforscher contest has taught me a lot, and there are especially 3 things I wanted to share with my fellow young scientists. The first lesson learned was that when signing up for the contest, one doesn't have to be an expert in the chosen field. One doesn't have to be a great scientist either. But getting started on a fascinating subject leads us that way. In the process, we learn how the scientific method works, how a paper is structured, how to defend the project in front of the jury, how to explain it to other people and to share it with the world. And to give an example, at the beginning of the contest I participated in, I didn't know that the theoretical information belongs in the introduction part of the project paper instead of the interpretation part. But I learned it along the way, and that's what matters. And a second lesson I learned, and which I find very important as well, the water analysis were made with aquarium tests. They were brought online at a very low cost. The microscope and the hemositometer were lent by my school. So you don't necessarily need a fully equipped laboratory to do good research. Because with quite basic means, I did get results I could work with. The aquarium tests weren't able to detect nitrates, that was true, but they did detect nitrates and phosphates. I did get results to work with. So doing science is really accessible to everyone. And finally, last lesson I learned was to try to see the strong points of our project. Because when working on a project, one does make mistakes, or at least I did. And we also always seek to improve our projects. And because we know them so well, and we also know the weaker points of it. This gives us the opportunity to work on them, that's right. But the risk is that we kind of miss the strong ones. And that would be sad, because we also have to defend our project in front of the jury. And while defending it, we have to point the strong points out. And so don't miss these, and try to be proud of yourself. Thank you.
Thank you, Mara, for this interesting presentation and sharing with us your experience. And I can also tell that you've put a lot of effort and thought into your research, so thank you very much. Now, let's please welcome Dr. Fista on stage with a big round of applause.
Royal Highnesses, distinguished guests, ladies and gentlemen, and fellow scientists, young Forscher. So it's really a pleasure for me to be here today. I told someone just before that it's for me the first time in about 2 years that I'm speaking in front of an audience. So that is also somewhat special for me tonight, and I would really like to really stress the point that Mara really did an awesome job, and you were facing these technical problems that we always face also at the big conferences, so don't worry about that. It was a great job, and I guess all this fancy electronic gear and audio systems, they are also kind of not used anymore to be at the conferences. So we are talking about the water futures today, and I will try in the next 30-35 minutes to give you an insight into all the work that we have done over the last 20-25 years. And so this is a very short view of the topics that I'm going to address today. So first of all, setting the scene, what are we talking about when we talk about global change and how the water cycle is impacted. Then also a few elements about what the water cycle actually is, so the components of the water cycle. Then very important, the toolbox that we have for investigating the water cycle. then you will see that we are still facing today a lot of difficulties in really understanding how the water cycle is functioning, and that we are sometimes facing technological limitations and that we try to overcome. And then also a few hopefully positive perspectives that I can give today. So, setting the scene. So this is one of maybe 2 or 3 a bit gloomy slides for today. So we all know that there's a climate change going on. Actually, climate has always been changing, so we should never forget that. But it is true that human activities have really, I would say, played the role of a catalyst and have really contributed to accelerate certain mechanisms. So we are clearly on a hothouse Earth pathway, and there's not that much time left to change that and to not go this way of the trajectory, but rather this way. So there's clearly toxic trajectories that we will face under future climate conditions if nothing is done to prevent that. We have 2 examples here. So on the left you see, and we experienced that last year, the heavy precipitation events that are very likely to further increase. So we will be facing other events like the ones we faced last summer. I mean, those are pictures taken, I think this one is from 2018 in the Müllertal, so where we had these severe flash floods. And we have on the other side also the increase in temperatures, and they will certainly contribute to increase the frequency of droughts, and that has severe implications, of course, for food production, I mean agriculture in a large sense, and of course also the wine production, just here as an example. So, very important, non-stationary is clearly in science today the new paradigm. What does it mean? Well, it means that, first of all, in the past, so we have been monitoring like parameters like air temperature, precipitation, atmospheric pressure, you name it basically. But the problem is, it's only very recently that we have started to measure more and more of these parameters, and also in many places all over the world, but it hasn't been like that in the past. So we lack understanding of how the environmental systems were behaving, for example, 200 years ago, 1,000 years ago. And that means that all the tools that we have developed, the forecasting systems, we push them more and more to their design limits when we ask them to help us anticipating how environmental systems are going to behave under a changed climate. So that is really the most tricky part that we are facing today in our research. So the water cycle, I briefly mentioned that I would like to introduce you to the main concepts of the water cycle. So you always have to keep in mind that we as hydrologists, we work in spatial entities that look like this. So this is a catchment, a river basin if you want. For example, the Alzette is a river basin that is part of the Sur river basin that is then part of the Mosel, and so on. And what we are looking at, it might sound trivial, but it's precipitation. So we would like to know with a lot of detail how much rain or precipitation in a large sense, snow is entering the system. Because then a part of that water will be taken up by the vegetation, will be evaporated, will be transpired. Another part of the rain will infiltrate into the soil. It might percolate further deep into the groundwater bodies. And then at some point, this groundwater will be released and feed the creeks, the rivers, the streams, and this happens all over the world, of course. And why is it important? Why does it matter to understand these components and how they interact? Well, because it tells us something about how floods are generated. It tells us something about the water balance in agricultural systems. So is there enough water, maybe too much water? Is there erosion maybe taking place? It is important for The trees, of course, that they have enough water. It is important in terms of agricultural production. If we have droughts, that, of course, may reduce the crop yield. It may also impact the water quality because when you don't have enough water in the streams, it means that the temperature is rising. It means that toxic substances, I mean, Mara was talking about it, then the concentrations, they may eventually increase, and that, in the worst case, might kill, for example, fish in the creek. So the water balance, with all its components, this is what interests us. And so this looks rather simple. As of today, the water that we have in a catchment is a function of the incoming rainfall, the incoming precipitation, minus the water that is leaving the catchment, minus the water that is transpired by the vegetation, and of course, plus minus the water that is already in the system and that might leave the catchment in a very deep subsurface, because these catchments are not necessarily completely impermeable, of course. So, after these introducing words about the water cycle, here's a very quick view of how certain catchments here in Luxembourg actually are behaving. So we have three different types of geology. You have the sandstone in green, you have the marls in red, and then the schists that are typical for the Ardennes in blue. Now, you can see here on these two figures very strong differences in behavior of these three types of catchments depending on whether a rainfall event occurs in winter or in summer. Just take a look at the sandstone. Actually, there's not much different between winter and summer as compared to the marls, where you have a very flashy response in winter and almost none in summer. Why is that so? Well, because the sandstone functions like a big sponge. It is just capable of absorbing the water regardless of how much rainfall is coming down, and then it gradually releases it throughout the year. For the marls, it's very different. It has a very small storage capacity, and that storage capacity is very quickly reached in October, November, and then you start to have these very flashy responses. Whereas in summer, well, they run dry, there's no water in those creeks, and therefore you see hardly any response there. The schists behave somewhat in between the two. It's again totally related to the geology. I cannot go here into all the details, but this is mainly meant to show you how the underground, how the geology is really controlling the way how our rivers and creeks respond to incoming precipitation. So now, please, can you just launch the movie? So here you see a movie that we have made with 15-minute images taken in a small creek in the Ösling. And it's really like a living organism, basically, right? That has a pulse. And we could go on with this and have the summer, and you would see how it runs dry, basically. So it's really the pulse of the catchment, and this pulse is changing due to global change. So, and that means we have an accelerating water cycle. There's definitely something going on that makes these systems overreact. So there's so much precipitation coming down in a very small location with very high intensity, and they just cannot digest all that water, and this is then what happens. You have massive surface runoff, a lot of erosion and damage that's taking place. So look at this picture taken in a forest in the La Rochette region. You see the naked bedrock. Everything has been washed away within half an hour. So this is massive. This is something that you would have seen 30 years ago in the Mediterranean region, but not here. So it really is an alarm bell ringing here. So is this going to be the new normal? Probably. So what is the hydrological toolbox that we have at hand? So for investigating the environmental system complexity. So here you see a simplified figure of what we call the critical zone. So where you have the atmosphere, you have the vegetation, the living organisms, you have the soils, water, and then the bedrock. And everything that happens in between these compartments, well, this is what we are looking at and what we try to understand, how water is actually moving through these different compartments of the critical zone. Now, there again, the difficulty is that you have plenty of, literally dozens of processes that are taking place at different spatial scales and temporal scales. So you have to, so unfortunately today we cannot go into detail, but you have to know so that the water that you see during a flood, like for example last summer, there was a huge flood, there's water in there that is a few hours old, but there's also water in there that is days, weeks, years, decades, and even hundreds of years old. So it's a mix, it's a blend of water. And that makes the whole system so difficult to understand as to really anticipate what compartments are contributing to building a flood hydrograph. Oops, I went a bit too quick. And we are very lucky in Luxembourg that we have this kind of nested setup where we have different types of geology, land use, topography that we span with our network of stream gauges, so where we measure the changes in water levels in the creeks and rivers. And this is something that has been a game changer in the sense that we have really gained an understanding of how geology controls the response of our systems, and that will allow us also to anticipate how adapted they are to respond to changing climate conditions. So depending on the geology, certain catchments will be very responsive to a climate change signal, and others will maybe exhibit actually no change in response. So what are the tools that we have? Well, we have for the meteorological parameters, we would have the classical tool like a meteorological station where we measure precipitation, wind speed, air temperature. Today we can also measure the size of the droplets, how fast they are falling, is it rain, is it snow, is it hail. We have weather radars, so they span very large areas where you then see the spatial distribution of the rainfall. For the surface water, we have, as you can see, colleagues of mine that go into the river during the flood, sometimes a bit risky, and they measure how much water is flowing through the river at that spot. And then we have special wires where we can then install an instrument that is measuring with a lot of precision the variations in water levels. We observe our systems also with satellites. Today you have certain satellites that can look through the clouds, and they can actually detect soil moisture, they can detect the extension of a flood. Within a few hours, you have all this information over huge areas, and, as I said, looking through the clouds with microwaves. Then we have tools for looking into the ground, classical, we can make boreholes, but we can also run an electric current through the soil, and that gives us information about what the structure of the soil is up to 80 meters down into the ground. We have certain tracers like isotopes, geochemical elements. I will say a few more words about that in a minute. So, very nice. We have this wonderful toolbox, but the problem is we have, unfortunately, limitations that we have to face, technological limitations. If I take rainfall, we measure rainfall with these small devices. You certainly have already come across some of these in nature. They are very small. They just cover 200 square centimeters. Now, they are very precise, but only in a specific location. So that means when you have a strong rainfall event, well, if you're lucky, your rain gauge is exactly here where the most intense rainfall has been fortunately detected with a weather radar, but you may also be completely off the wall, like we were here. So there were only 2 stations, not really in the center of the heavy rainfall event. And so there's many other difficulties actually related to the way how we typically classically measure rainfall, but this is obviously the most important one. Then very important to us also is to understand like how saturated areas develop, because in those areas you won't have any rainfall infiltrating into the ground. It will all run off the surface and rapidly reach the creek. So the tools that we have is looking at the vegetation. We can also walk around and see if the soil is muddy, but this is very coarse, it's very time consuming, and so there clearly is a limitation in that respect. Then I said that we have certain tracers. We have geochemical tracers, so looking at certain elements that are dissolved in the water, and they can actually allow us, in this specific point, to really know from where the water is coming in the catchment. So geographically speaking, we can say so and so many % are coming from 10 kilometers upstream or only from 2 kilometers from the outlet of the catchment. Then we have the isotopes. So basically oxygen and hydrogen. So we have instruments where we can determine the isotopic signature of the water, and that helps us to determine how old the water is. Is it really precipitation, so the rainfall that has fallen in the few hours before that has reached this spot here, or is it maybe water that has fallen a few weeks ago? Because actually this is what happens in nature, and this is why we speak about the old water paradox. So having a flood wave, but it's mostly made of old water. So, a difficulty there is that, and this is a colleague from ETH Zurich who had a wonderful paper on this, he was saying that actually what we are trying to do with the tracers, with the rain gauges and all these nice instruments that we have is like trying to understand the Beethoven symphony if we could only hear one note every minute or two. Because it's really just patchy information that we get. And this is also what happens when we go to the field and we take water samples. We bring them to the lab, we do the analysis, so it's very coarse information. And when we talk about flash floods, you can imagine that if you go once per day, even once per day, to a specific spot, you might just miss the flood wave. And so you lose the information. So how can we overcome these challenges? Well, I come just back one second to what I said at the beginning. So we have this limitation that our tools are kind of inappropriate. They are pushed beyond their design limits, right, for anticipating what is going to happen in the future. So what we need is, first of all, new hypotheses, so new ways of thinking how the environmental systems are behaving, have been behaving in the past, how they behave today, and how they might behave in the future. Then we need new technological developments for testing these hypotheses, and from those experiments, from those hypothesis tests, we can then infer new concepts of how we perceive the environment to function, and we translate them into mathematical equations and into programming language so that we can build digital twins, like we call them, of the critical zone. That will eventually be the tools of the future for better anticipating where we're heading. Are we on the hothouse Earth path, or can we still, when we take certain measures, avoid this gloomy scenario? So, therefore, we have in our institute, we have developed a kind of research value chain where we do basic research, so these new outrageous hypotheses, then we try to develop new technological solutions for testing these hypotheses. They help building the digital twins of the critical zone, and that leads to more robust predictions of the future. So a few examples of outrageous hypotheses. I give this example because it's very telling. So a few years ago, we stated this hypothesis of having bedrock geology being really the major control of the hydrological functions of the catchments, meaning collecting the water, storing the water, mixing the water, and gradually releasing the water. So those are the fundamental hydrological functions of catchments. And for that, we use the isotopes of the water molecule. So oxygen is not oxygen. You can have oxygen 16, 17, 18. So being a little bit more heavier, so 18 is a little bit heavier than 17, which is a bit heavier than 16. And we do the same, by the way, with hydrogen. And so we measure those concentrations in precipitation, as you can see here. So those variations correspond to seasonal variability in the precipitation signal in the isotope signal in precipitation. And then you see what the catchment does with this seasonal variation. It transforms it so that the amplitude is reduced and there's also a time shift. And these two informations help us to actually infer the age of the water. And so on the water release aspect, we have been, and this is the first time this was done worldwide, so we were able to show that depending on the percentage of impermeable bedrock, the mean age, this is the mean age of the water, is actually decreasing. So those would be catchments that have impermeable bedrock, typically marls, so very young water in comparison to catchments where you would have a higher percentage of permeable bedrock, so typically sandstone, and there you would have higher water age. Why is that important? Well, if you want to use, like the city of Luxembourg does, they take 50% of their drinking water from the Luxembourg sandstone. That water has been traveling for decades through the sandstone, and it's a wonderful natural filter, so it's good quality water that you get there. Here, in those young waters, you have all kinds of contaminants, of toxic substances that might be present that have not been filtered out. So this has been published in the meantime. There's many colleagues from our institute, but also from Canada and New Zealand that have contributed to this. So the high reward, high risk, high reward technological developments. So I guess, a few years ago, I would ask the question, who has a mobile phone in the room? Today, you can't do that anymore. I would say 99% of the people do have a mobile phone. What makes it so special? Well, actually, your mobile phone is like a rain gauge, because these antennas that are used for transmitting the microwave signal, they are influenced by precipitation, by rainfall. So what we did is that we installed, together with Post Luxembourg, we installed 2 microwave links, experimental microwave links. Then we had these violet dots here, they represent the rain gauges. So there we were measuring precipitation, so to have a kind of ground truth information. And you see here, when it rains, the microwave signal between the antennas is weakened. And we were able to translate that weakening of the signal into precipitation. And that means that instead of having this dotty information, we can, with these microwave links, and there's plenty across the landscape, you can reconstruct at a very fine time scale and a very high spatial resolution, you can reconstruct incoming precipitation, which is a game changer when it comes to forecasting a flood. So, another example is thermal infrared imagery. Look at this creek. It's the Weierbach in the Ösling. So when you look with a thermal infrared camera, you can see this. And this is all red, showing the high temperatures. And this is actually what I mentioned beforehand. It's the old water that is leaving the hill slope because it has been raining in the hours before. So the new water has infiltrated and pushed the old water out of the hill slope. So that is what is happening here. And that is feeding actually the river. So a very important information. So maybe you can just very quickly run this graph too, because here you see in a headwater catchment, so really upstream, how a flood wave is actually generated. You see how the water is gradually pressed out of the hill slope. So with the colors getting brighter and brighter. So first time that this was documented ever was here in Luxembourg with these tools. So we have another avenue that we have explored together with the colleagues in the material sciences department. We were really wondering, so it is so cumbersome, so difficult to go to the field, to take the samples, bring them to the lab, do the analysis. There's literally days between the moment where you do the sampling and where you get finally the analytical results. So the idea was to develop with the colleagues an instrument that we could take to the field and do the measurements directly in the field. So this is the small-sized mass spectrometer that eventually actually has now been further developed by the colleagues in the material sciences department in the framework of space resources related projects where they would hopefully one day have one of these instruments measuring stable isotopes of oxygen and hydrogen on the moon. So this is what I was just mentioning, a new field of research that is developing, Exo Hydrology, so studying the water cycle on another planetary body. And we have started 2 years ago, from those technological developments that I mentioned, a project where we will work together, where we actually are working with the European Space Agency and now just kicked off our participation in the science team with NASA, where we are looking at water pools on the moon. And there's different reasons for that. You might use the water on the moon for producing rocket fuel. You might also, for future lunar bases, you need fresh water. And so this is the mission called Prospect that we are actively participating in. And we're really looking forward to that with a great deal of anticipation. It's really genuine technology developed in Luxembourg that will be used for making the models that are needed for translating actually the measurements that are done on the moon into useful information in terms of how much water is there, where exactly is it located because it's not evenly distributed, etc. Another crazy idea, if I might say so, that we have been investigating is to overcome the fact that we have very little time series of isotope signatures in stream water because, as I said, it's very difficult to obtain them. You have to go to the field, take the samples, bring them back to the lab, etc. So we thought, well, maybe we can use organisms that live in the rivers as archives of isotope signatures. So they live there all the time, and they might take up the isotopic signature of the water in their shells. And so we could overcome this limitation because certain species of freshwater mussels, they can live up to 200 years. 200 years. So we could go back 200 years in time. So that's what we did with the colleagues in the material sciences department. They have these instruments where they can throw an ion beam on the growth rings. So this is 1 year. They can have these ion beams hitting a growth band, and you see these dots. Then the isotopes are, it's like an explosion. They are broken out from the growth ring. They go into an electromagnetic field, and they can measure, is it O16, O18, etc. So we have in the meantime been able to publish this methodology and to show that it works regardless which climate you're in, different types of species of mussels. And so now we have a project going on where we will, for the first time, reconstruct these long series in Luxembourg. And the idea has already been picked up and also tested in other environments, like, for example, in Sweden. So now, very quick, how can we translate all that newly gained knowledge into the digital twins, so the forecasting systems for these extreme events that I mentioned? So look at these images. So they are from Austria, but still this is exactly what was happening also in 2016 and 18 in Luxembourg. So these kind of really very intense local rainfall events where very large amounts of water are pouring down. And so what they generate, especially of course in hilly regions like the Alps, we can see that over here, if you just run that movie too. So this is really spectacular. Unfortunately, we don't have that kind of camera that has been around for observing that kind of event. But this is typically, even though at a smaller scale, but you can still see the rills in La Rochette, where a kind of similar process took place. So, and there it's quite obvious that it's important to better understand the processes that are leading to such extreme events. Of course, again, you have to place this in the local context, this in the Alps. The rainfall intensities are even much, much higher than what we have observed here. So we had recently a project together with the Water Agency and Post Telecom, where we have tried to rely on new technology so related to IoT, so the Internet of Things, the idea being to have more stations that could potentially also be mobile, where you could adapt your rain gauge network, and so to have more timely information feeding forecasting systems. And so to be able, because especially in that kind of context, every minute almost that you gain can be a game changer in terms of saving lives and saving infrastructure. And also, what is very important is that these new technologies have also helped now with very powerful computational systems to make projections of how the climate might evolve in the coming decades in Luxembourg. And you can clearly see that we are definitely on this trend that you can see elsewhere in the world. And if nothing changes in terms of emissions of greenhouse gases, this is where we are going to be. So we are going to gain another degree and a half in the next 40, 50 years. And if we look at precipitation, this should not mislead you. Here you see the projections for precipitation. It seems like everything is okay. No, it's not. Because what we have indeed seen over the past decades, and this seems to be also the trend for the coming decades, is that we might not necessarily have less water, annually speaking, but it's very likely that it will be distributed in a different way. So more intense rainfall events, which has you at the end of the year with the same amount of rainfall that came down, but it has been distributed in a different way. So a greater likelihood for heavy floods, and on the other hand also a higher likelihood for droughts. So, well, basically this is already what I just mentioned. And so the perspectives. So we really would like to have our research being used as a sound scientific basis of information for detaching the socio-economic development that we all want and that we all need from the environmental pressure. So that is really why we're looking into these problems, why we try to find new avenues for overcoming the technological limitations that we are facing. And well, as I also said at the beginning, we have developed a value chain where we really span this whole chain of developing new sensors, generating new types of data from which we can extract more information, different types of information that will then eventually be transformed into knowledge, and that knowledge will inform the decision makers that will be able to take better actions. So, and of course, all of this, I mean, I'm just a messenger. So all this work is done by nearly 60 people. There have been generations of students before, so that were before all these people over the past 25 years. So many PhD candidates, postdocs, engineers, technicians. And without them, without their power of interdisciplinary approaches, it would just be impossible to tackle all these aspects. So, thank you very much for your attention, and yeah, I'm open for whatever comes next, questions or...
So thank you, Dr. Fista, for this enjoyable and thoroughly informative presentation. Now that we've all been well informed on the quality of water here in Luxembourg with the respective presentations of Mara and Dr. Pfister, I would like to ask some questions that I've had during these presentations, and of course encourage you, dear guests, to ask any questions that have popped into your mind throughout the whole conference. So I'd like to invite our scientists to the stage and to take a seat with me. So, of course, if there are any questions already from the audience, please reach out and we will make sure to provide a microphone. And if not, I will begin with my questions then. So I have a question for both of you, Dr. Pfister and Mara. I would like to ask about your personal engagement with your research. So what encouraged you to personal environmental science or environmental research for this specific occasion?
Ladies first.
Okay,
Mara, go ahead.
thank you. So while I consider myself part of the Greta Thunberg generation, so to speak, so I think growing up nowadays, young people have gotten more of a sense of, a better sense of the world and a sense that the climate is evolving, and I think that we quite have an awareness of climate change, and so the environment is important. We live in it, so it is an important part of our lives. So yeah, one asks questions about it, and sometimes it's nice to find answers.
Yeah. Okay, thank you, Mara. And you, Dr. Pfister?
Well, so in my case, this is already almost 30 years ago. And actually what I wanted to do, I wanted to be, in the first place, a high school teacher in geography. And then it turns out that when I had almost finished, so I was finishing the master thesis, there were these severe floods happening in the Alzette and Sur River Basin, and the government actually published a call in the newspapers where they were saying, well, we're looking for people that would be interested in helping in finding new ways of how events like those could be tackled. I mean, back in those days, there were questions in the room like, well, is this already climate change, or is it the land use change that caused these floodings? So we didn't know. And then also the government opened the possibility, they gave the possibility to young people like me back then to get a funding, a fellowship, for doing a PhD. And that was a game changer. And I said, well, I have to try this. And then, it would take an hour, I guess, but it was wonderful to see that at some point we had the National Research Fund created, and a huge momentum developing, and it was wonderful, and it is wonderful to be a part of it. And it was just a conjunction of, situations, opportunities that brought me there.
Okay, thank you for your answers. I think that was very interesting. And would there be a question about these from the audience, or a comment on the answers from our scientists? I think there's a question over there.
Yeah, the photographer has questions. I was listening to your presentations, very interesting indeed. The feeling sometimes when we hear bad news at the beginning, even though that we see that there are some researches going on and that there is a new generation taking on the topics, sometimes we have the feeling that we, profane, can't do much about that. Although, like, there are plenty of new tools out there. I'm thinking, for example, about astronomy, which is a field that I particularly appreciate in terms of science and stuff. We see initiatives where people are able to use their own computer or their own mobile phone to actually help, calculate or provide with some computing power. We see that in medicine as well, biology and stuff. Are there any similar initiatives like to help prevent maybe floods or this kind of catastrophic scenario, or maybe a positive scenario simulations that we would like to do actually?
I mean, what I can say about this is that there's initiatives now going on that relate to citizen science and that are generating really highly useful data. I can give you an example of a colleague of ours. He launched a project a few years ago where they invite people to use their mobile phone, take a picture of a stream gauge, and then they send it to a specific address where that image is automatically archived. There's an algorithm that reads the image and archives then the level of the water stage in the river, and that is feeding directly into a model, that is fed directly into a model, a hydrological model, for doing predictions, right? And this is a very beautiful example. We've done something slightly similar, asking high school students to sample rainfall. And they would build their own rain gauges and then send us the samples, and we would do the isotope analysis. So it's not, how to say, it's still very early days. I think we are doing not as good as in astronomy, for example, and there's a lot of potential that is still untapped and that we should definitely look into. Yeah.
I think there are some other questions as well.
I have 3 comments. The first one is to thank you very much for delightfully enlightening presentations by both of you, and to thank Carlo and his team for Science Next. This is really something which is also very delightful. I worked on sensors in the past, and the second comment is, you mentioned, Dr. Priester, you mentioned that you use oxygen-18 and tritium. These, of course, give you different timelines about how old the water is, which reminded me of, I think there was a workshop in 2009, 2010 at the International Atomic Energy in Vienna, maybe. And the proceedings were very similar to what you were talking about, except that the metrology that you're talking about is so well advanced now compared to 2009, 2010, which is huge development. And I think what's important also to what Mara said is that you cannot also rush good science unless if you throw huge amounts of money at it. You're not like astronomy, they have not thrown huge money at you yet, but maybe the time is coming now where with these catastrophes and with these extreme weather changes that are taking place, then there will be that development. So the final thing which I wanted to ask you about is the modeling of these things, because you talked about the methods, you talked about the tools. Now, to model these things must be a real nightmare. You have so many multi-factors coming into there, so to try and develop a universal model for everything is not easy. You have steady state limitations, you have dynamic limitations. How far is the, again, I mean, this is from pure ignorance, how far is the system developed now to enable you to start modeling, for example, when I open my tap in the morning, my water, I can tell it's old or it's new, yeah? How far can you, that's a very simplified question, how far are you from being able to be actually very, as quantitative, as qualitative as you can in terms of both of these systems?
Well, this is, first of all, thank you very much for the question. It's not easy to answer that question. We have made a lot of progress on transit time modeling, meaning 10, 15 years ago, we would say we have, when we were talking about water age, so we would say the mean water age in a river or a spring is, I don't know, 10 years, 20 years. Today, we would not do that anymore. We would rather say that it's a mix of waters, of different ages. And we have now rather sophisticated models that allow us to quantify, or how to say, to identify, to characterize the blend of different waters of different ages. And because this changes over time, this assemblage of waters of different ages changes over the course of one day, of a week, of a month, a year, etc. Because you have never exactly the same amount of rainfall that is falling, you have the seasonal differences, etc. So this is something that we are more and more capable of doing properly. And the tricky thing is, so this is just one aspect that relates to water quantity. Then you have qualitative aspects that come into play. That makes the whole system more difficult to simulate, especially on the long run when you look into the future. And we are not there yet, very clearly. But we're working on it as a community, right? So.
Thank you very much. So I think there was also another question from the audience.
Hello. First I wanted to congratulate Mara for her fantastic work, and gives me good hope, because one of those conclusions that I would draw was that climate and environmental protection in Luxembourg really works, right? My question for Dr. Pfister, you mentioned that we are in the middle of climate change. Obviously, we don't have winters anymore. We don't have enough snow out there. One often reads that snow is very important to fill up our reservoirs because water goes down more slowly. At the same time, you tell us tonight that the distribution of the rain across the year will not change, but it will be very more heavily or intensely on one moment than the other. So that would imply that water would run into rivers and again, not anymore into our reserves. Do we have to fear that there will be a water scarcity in the future, considering that our population is very dynamic, industry, everybody uses water? Do we need to think about constructing new water supplies? And where would they be in Luxembourg?
Well, for the first part of thank you for the question, and for the first part of it, I think it would be foolish not to take into consideration that there is this redistribution taking place. There is the rise in temperatures, there will be higher losses by transpiration, evaporation, and this will inevitably impact our water resources. And it would not be a smart move to just let things go and not try to anticipate what we can do about it. Now, what to do and where to do it, this is clearly something that I think I'm not the right person to comment on that, because this is typically what the water managers are supposed to do. What we can do is give them the information that something is taking place, when it is taking place, when it will take place. Of course, the tools that we develop will help them to assess the impact that some of these counteracting measures may have. And then based upon that, they can take a decision of rather going for, I'm not just brainstorming, building a reservoir or I don't know, replanting trees or whatever, that kind of decisions. But that goes beyond our, how to say, our field of responsibility, let's say, right? Yeah.
Thank you very much. I actually have a question for Mara. So just to think a little bit about what you mentioned, do you think the efforts of the past generations of scientists and policymakers, like you said, have been sufficient in ensuring sustainability of resources? Or to also think about one more aspect, will you pursue environmental research in the future? And if you will, what would you like to see the next generation of scientists collectively achieve?
Okay, thank you for your question. So, to answer to the first one, which is a rather political one, while I think the awareness of climate change and the environmental change has really happened in the last years, in the last decades, and so policymakers follow the evolutions in society. So change has really happened in the last decades only. So perhaps we would need to work a bit more on that in the future or right now. For the second question,
I can repeat my question.
Yes,
So I want to know if you will pursue environmental research in the future, and if you do, what would you like to see the next generation of scientists achieve together?
well, I'm studying medicine right now, but medicine is a broad field, so one could easily imagine doing something like environmental medicine. So perhaps, yes, medicine with a bit of environment. And I mean, what would be nice to see achieved? The whole research and environmental research has still so many questions and so many things that can be researched, and so many things that can be done. And well, it would be nice to see these questions answered, worked on these, because as Dr. Pfister pointed out in the presentation, there are still challenges, for example, for the future provisions, and answering these questions would be nice.
Okay, thank you very much. So I would like to ask lastly if there are further questions from there's one over there.
Thank you for the presentation and all your work you have done. I still have a question for both of you. How would you evaluate the overall water quality here in our Luxembourgish rivers and the drinking water sources in comparison to other countries?
Can I go first?
Yeah.
So, as for the drinking water, I would say that it's of very good quality. This is clearly something that we see. We have been working with the city of Luxembourg, just as an example, for more than 20 years. So, monitoring not only the quality of the water coming from the springs, also like how they behave, how quickly they are responding to droughts and to periods where there's more rain coming down. And the quality is really good. Honestly, our tap water is and not only in Luxembourg City, generally speaking. Of course, there can sometimes be events happening like intense rainfall that locally causes problems with bacterial contamination, but it is so exceptional and usually measures are taken very quickly. So I would say there we are really well positioned, and we should make sure that we keep it that way. And again, I can only take the example of the city of Luxembourg. They are putting a huge effort into that. And of course, we have the water agency that is looking very closely at these aspects. So, yeah.
And the quality of the water in the rivers as well is also quite good. In the project, I studied the concentrations of nitrates, and phosphates, which are only 3 ions. So there are also other things in our rivers. But I think the concentrations are found are still very good compared to the maximum concentrations you can have for drinking water. So, and if we think about the river waters, which whose main use isn't for drinking, and if we still have quite low concentrations, even if we see the variations over the year due to agriculture or industry, the concentrations are still quite low. So I think the river water is also quite good. Or what do you think? Also,
well, I think it really depends on where you do the measurements. Like there's some spots that I remember we've been looking for many, many years at the Petrus in Luxembourg City. And there you had the problem of the so-called first flush. So when you have had a dry spell, say, I don't know, 3 weeks, 4 weeks of dry weather, you would have the tire wear on the streets, maybe some oil dripping off the engines and all kind of dust particles lying on the streets. And then when it's raining in the very first minutes, typically storm event in summer, all this is washed off in a few minutes, and it goes just within a fraction of a second. It goes into the pipes and reaches then in a few minutes the Petrus, and from there the RZ. And that creates these first flushes of pollution that are a disaster for fish or whatever you might find in the RZ. And this has been really dealt with again with big projects that have been carried out in the last, I would say, 5 to 10 years. And then there's also the renaturation of the Petrus that is currently going on. This is also again a huge step forward in that respect. So yeah, but again, you might have the overall situation, and then, of course, in some locations, very tricky problems that need specific solutions.
I think the floods with the extreme weather events that are going to be more and more often, the floods they take everything that is in their way. So afterwards, we might have more polluted rivers as well. So it might really depend on the time when you are looking at the river.
If I may just compliment,
yeah.
We have a wonderful project together with the University of Luxembourg going on, so a collaboration between LIST and the uni, which is called the Luxembourg Time Machine, where we're looking at the history of the flowing waters and the groundwater in terms of, so we all know that in the south of Luxembourg there has been a lot of industrial activity going on. It's very important for the country, but there's also legacy related to that in the sediments, in the water, groundwater, surface water. And this certainly also is very closely connected to the socio-economic history going back 100 years, 200 years, and implications for public health, on vegetation, on animals. So this is a very nice project that is currently going on in that respect. So just to mention.
So thank you very much for your answers. Would there be any more questions from the audience? I think there is 2 more. One more here.
First of all, it was a pretty wonderful presentation. And what I learned is that water is very important. So my question would be, is there anything that we can do in our everyday life just ensure that the quality tastes good? I may not be a farmer, so all the pollution around fertilizer. Is there anything that we can ensure that we have clean water?
I think you have to answer first, because I still have to think about my answer.
Okay. Well, there's probably a few ways, several ways to look at it. I think we should all take the water for what it is, a very precious resource. We live in a country where we're fortunate enough to have enough water, at least for the time being, but that doesn't mean that we should use it in in a non-respectful way. So use as much as you need, but don't overuse it in a certain sense. And so that's the first point. The second point I would say is we have all of us, we have to understand that water has a price. It is when we take a shower, when we go to the restroom. I mean, the water gets treated in the wastewater treatment plants. This has a cost. And so we should not complain about tax money that goes into the construction of new wastewater treatment plants, because we also have to understand that our way of consuming has eventually the wastewater treatment plants it's almost like in doping. So there's always new substances coming up and you have to deal with them. And it's an arms race. So there's new molecules coming up and you have to get rid of them and you have to develop new filtering techniques. And so this has a certain cost and we should not complain about it. It's just part of the game. And also, that's maybe the third part of my reflection, is that we should ease a little bit the pressure that we put on on politicians, in the sense that, well, if we sanction politicians each time that they take decisions that are, that are sort of constraining our freedom in using natural resources, we should give it a second thought and not react in a spontaneous way and say, oh, I'm not going to vote for this guy anymore because he made me pay more taxes for this and that. It all comes with a cost. And because that then also paralyzes sort of or it may at least paralyze decision makers because they get afraid of taking unpopular decisions. Just my thought.
Would you like to add something?
Yeah, I think there are the known measures of not wasting water. So apart from that, I think I don't have anything to add.
Okay, thank you. And any more questions? There's one question over there.
Yes, so how how do you quantify the balance between economic, for example, growth and environmental measures? For example, if they may have negative impact on economic growth, how do you quantify the balance?
I'm not 100% sure that I got it.
Could you maybe repeat your question?
How high should the cost be for environmental measures?
Well, that's a tough one. Huh? I mean, of course, it has to remain. This is really a tough one. I mean, it has to cost what it has to cost. I mean, because there's the public health also involved. I mean. Again, if we as citizens, if we as consumers think about it and try to behave in a responsible way, then hopefully we don't have to take these very costly measures, right?
Yeah.
So, not sure if that is a satisfying answer, but that's how I see it.
So
It is.
It's hard to answer quickly.
Absolutely.
But thank you
You're welcome.
for the presentation and this conference in general.
Thank you for your question and thank you for your answers. So with that, I would like to thank you for the insightful presentations and your time. So we just wanted to thank you for your time and
Merci.
Thank you. So, ladies and gentlemen, your Royal Highnesses, dear young scientists, thank you so much for your participation in this wonderful event this evening. I would also like to thank our audience watching online on the live stream. If there are no further questions or comments from the audience, I would like to invite everyone to the hall for an informal exchange and networking space with our board members and Jungforscher over some refreshments and snacks. And I wish you all a great evening, and thank you very much.